In example 2, we're going to determine analytically whether Rolle's theorem applies to the following functions. If so, find the point guaranteed. So we need to make sure that those three conditions apply. So condition 1, continuity. So in for condition 1, we can say that the domain of f of x is any number can be cube rooted or squared. So the domain of f of x is all real numbers. Therefore, f of x is continuous on negative 8 to 8. Okay, that's the first condition. We need to state that we are continuous and what our reason is. Now, second, we need to talk about differentiability. So let's find the derivative. And so the derivative, f prime of x, is 2/3 x to the negative 1/3. That's the same thing as 2 over 3x to the positive 1/3. Okay, now that's not continuous at 0. So f prime of 0 fails to exist. So that means that f of x is not differentiable. On the interval negative 8 to 8, because 0 is in that interval. So Rolle's theorem does not apply. We failed condition 2 because we found a point where the function was not differentiable that is in the open interval that we needed here. Okay. So now, if I look over here, I can see that there is an extrema, but it's not a smooth extrema. This is not a place where I have a horizontal tangent. So the derivative is not equal to 0 there. All right. So Rolle's theorem does not apply there. We're going to have to stop with that one. We can't guarantee the existence. There is no point. No C value. So let's see what we can do with the next one. Okay. Let's see. 1. Okay, so the domain of f of x, or g of x, sorry, is, okay, now this is tangent. And so tangent is sine of x divided by cosine of x. And so if you let the geometry equal 0, cosine of x equals 0, you're going to get x equals pi halves, comma 3 pi halves, comma, etc. So the domain of g of x is the set of all x such that x is not equal to odds, so 2k plus 1 pi halves. Now, if our interval of interest happened to not include one of those pi half values, then we'd be okay. However, pi halves is in the interval 0 to pi. So we have to conclude that, I keep wanting to call it f, this is g. G of x is not continuous on the interval 0 to pi. Okay, so Rolle's theorem does not apply. Okay, so these are two cases where I cannot get to all three of my conditions, and therefore I cannot guarantee the existence of the point that has a horizontal tangent. As you can see from this picture, there is no point with the horizontal tangent in that interval. Now we're going to look at a point where hopefully I will be able to verify the three conditions. So determine analytically whether the theorem applies, so prove it does. If it does apply, find the points guaranteed by the theorem. All right, so my three conditions. First, I need to talk about the domain. So h of x is polynomial, so it's continuous in all real numbers. h of x is continuous on all real numbers because it's polynomial. And then we can say, therefore, h of x is continuous on the interval of interest, which is 2 to 3. Okay, so we have our justification for the first criteria. Second criteria. All right, now I'm going to need its derivative. This derivative might be easier found if I multiplied it all out, but let's actually go ahead and do that since we're going to want to find the point anyway. So this is, okay, so there I've got it multiplied out, make it easier to find the derivative for us. So the derivative h prime of x is 4x cubed minus, I forgot to do the derivative. I was writing the original function again. Goodness. Okay, so it's going to be 12, there we go, x squared minus 48x plus 44. There we go. So that's the derivative. Sorry, I started writing another original function again. Okay, now the domain of h prime of x is all real numbers, and we can conclude that therefore the original function h of x is differentiable on all real numbers, but particularly on the interval of interest 2 to 3. All right, so that satisfies condition 1 and condition 2. So condition 3, we're going to be checking that the left endpoint equals the right endpoint. So h of 2 is 4 times 2 minus 1 times 2 minus 2, that's 0, times 2 minus 3, so that's 0. And h of 3 is 4 times 3 minus 1 times 3 minus 2 times 3 minus 3, that's also 0. Again, they don't have to both be 0, they both have to be the same as each other. So they could both be 6, but as long as they're equal to each other, we've got it. So we can conclude that therefore h of 2 is equal to h of 3. All 3 conditions are satisfied. Once all 3 conditions are satisfied, we get our conclusion from the theorem. We get to say, thus, there exists a c in the interval 2 to 3 such that f prime of c is equal to 0. Okay. That finishes Rolle's theorem. Rolle's theorem has 4 parts. It has proving condition 1, proving condition 2, proving condition 3, and making our conclusion. Now, what we were asked to do was first determine analytically whether or not Rolle's theorem applies. We've done that. It does apply. Now we're at the if so part. If so, find the points guaranteed to exist. Verify the results graphically. So now I take f prime of c, set it equal to 0, and solve it. It's not f, it's h. Sorry, h prime right here as well. This is h. All right, so h prime, I've already found it up here. Setting equal to 0, let's factor out 4. So I have 4 times 3x squared minus 12x plus 11 equals 0. That doesn't look factorable, so quadratic formula. X equals 12 plus or minus square root 12 squared minus 4 times 3 times 11 over 2 times 3. Let's go to a calculator real quick. We need to do 144 minus 4 times 3 times. Okay, so that's 12 plus and minus square root of 12 over 6. So that simplifies to 12 plus and minus square root of 4 is 2, square root of 3 over 6. So 2 plus and minus the square root of 3 over 3. Okay. Sorry, I was writing on the other screen. And we're back. Okay, so got that all simplified and pretty. So the existence of the points should be at, I just need to find the C value guaranteed. So I want to see if either of those is in the interval. So back over to my calculator for a second. Oops, wrong. How do I keep popping that one up? There we go. All right, so I want to find out if 2 plus the square root of 3 over 3 or 2 minus the square root of 3 over 3 is in the interval. The interval was 2 to 3. So this one is not in the interval. It's too small. 2.57 is in the interval. So we can conclude that the point that we were guaranteed in the interval is 2 plus the square root of 3 over 3, because C equals 2 minus the square root of 3 over 3 is not in 2, 3. So that's the point that we were guaranteed by Rolle's theorem. We were guaranteed that there was a C value between 2 and 3 such that the derivative was equal to 0. We got two choices once we solved. One of them was not the one guaranteed because it's not in the interval. That's the one that was guaranteed by the interval, so we found it as well.